Hey, good morning. Welcome to the second session of Reliability Engineering. And today we are going to proceed with dependability of mechanical systems. As we can see here, that was a very severe accident, and it was the result of the failure of a single component in a very complex system. And what we treated last time was the question why such a thing could happen, and also what are specific risk factors for this. And so we have seen that it is important to know what the load is. If it is just a monotonously increasing load, as we can see it here, so it just goes up until we reach the ultimate tensile strength, for instance. On the other hand, we can have alternating load. It could be, for instance, a harmonic load or a superposition of many harmonic loads, like it is in the vibration of the blade of a wind turbine. And engineering means we must take into account these conditions as precise as possible, and to have models which are as good as possible in order to predict reliability. Reliability in this case means how long it will live, and for the lifetime we can have several measures or several properties which can be used. For instance, in a car we could use the mileage, so how many kilometers it has been driving. On the other hand, if we have an agricultural vehicle, will we count the mileage, or what is relevant for the age of such a vehicle? Do you have an idea? So in that case, it would be, for instance, the hours of operation. So normally, in most cases or in many cases, we talk about hours. On the other hand, the lifetime in the case of cyclic load is typically measured in numbers of cycles. So that means how often we repeat such a load up, load down cycle, and when we count these, of course, we can end up with numbers between a few one and hundreds of thousands or even hundreds of millions of cycles. Okay, today we will see how to deal with such conditions. The basic knowledge we need to have is so-called Wöhler's curve or Baskin's SN curve, and we will see in more detail what that means. Second factor which is important is the question of notches or cracks. So that means at the tip of a notch or at the tip of the crack, the stress is increased. We have in brittle materials, we have a real singularity, so the stress goes up very high, and the increase of stress is the higher, the longer this crack or notch is. So that's this length here, and the sharper the tip is. That is important. And we can also see it from this simulation that was a graph which was produced by one of my PhD students. It clearly shows that we have stress concentration at the stress tip, and also it depends on the question if it is tension or if it is shear. Now you could ask yourself, is there also a stress concentration when we press onto the crack? And of course there is not. You can address this like you have a book. You press on the book, but it will not fail. The leaves will not even slide against each other if you just press in a perpendicular way, but you can easily take apart these leaves, and that means the energy you need in tension is much lower when you want to separate this contrary when you press on it. And also it is a good idea to keep in mind that a brittle material typically has a low energy of fracture. Brittleness is yeah, please repeat your question. Excuse me. Yeah. Then I still was. Yeah, I knew something. Okay. Sorry. Yeah, I noticed it. Sorry. Okay. So we have this stress concentration, and it also can be described by the so-called Snedden equations. Okay, let's go into a little more detail of this. And for instance, that is an example of one of my PhD students. When you look at the edge of computer chips made of silicon, then you typically can find very small cracks. So these cracks can be in the form of so-called chipping, as you see it here, but it can also be cracks going perpendicularly into the material. And now it has been found that you can describe such a crack by the lateral extension C, but the most important thing is here the depth with which it goes into the material. And in the case of silicon, it has been found that the stress at which silicon will break in tension is roughly 1.5 times the so-called fracture toughness divided by P and the square root of A, so divided by the square root of the crack depth. That means the smaller a crack is, the higher the breaking strength is. So now you can address it in a way that you say for brittle materials, again, brittle materials are materials which have a low fracture energy, but typically a relatively high Young's modulus. For such materials, you can define the fracture stress, and that is no longer depending on the material alone. That fracture toughness is the material property, but on the other hand, it is also a result of the crack lengths we have here. And now, using this simple formula, we can compute, and please note, we have taken a crack length or crack depth measured in micrometers, and when we take just normal silicon, when we have a crack of 1 micrometer, so it's almost crack-free, but not really, then we have a fracture stress of 700 megapascal. Going to 3 micrometer, that has a fracture stress of 410 megapascal. Again, going higher by a factor of 3 in crack depths, it's only roughly 200 megapascal. And going to 30, we have only a stress of 129 megapascal. Now, do you have an idea what is the tensile strength of just a normal construction steel? Can you give me a value? Now, taking from 129 to 711, where is the typical strength of a construction steel, for instance, which we use to make the skeleton of a tower building or such a thing? Give me an idea. What do you think? No idea? So a typical constructional steel is around 400 megapascal. So that means silicon can be very strong. When it has no cracks at all, you can go to strengths of several thousand megapascals. But on the other hand, when you have a defect which is 30 micrometers, you are in the order of stress of 100 megapascal, and 100 megapascal is a stress which can typically occur in assembly and packaging. So that means when you want to have reliable integrated circuits, for instance, then you must avoid any cracks on the chips, because these will degrade the strength significantly. Okay, so we also see that a crack is very important, and a crack can be very crucial for the survival probability of a device. Now let's have a look here at fracture toughness of materials and the yield strength. So what is yield strength? When you pull a material, at some point it will yield. That means it will deform in a plastic way. So if you release it, then the deformation will not go back. So it's a permanent deformation, and the point of stress when this starts, that is the yield point. So most devices will be destroyed when they started to yield, yes? For instance, because a precision part has lost its shape, for instance. And now you could say generally, when the fracture toughness increases, it increases with yield strength. That is mainly for, let's say, some polymers and especially for metals. Yes. So here, typically, all of these are metals. When we look at structural ceramics, for instance, we are here in a range from 1,000 to 10,000 megapascal. We can also have so high strength for glass. That's the reason why nowadays glass is used for, let's say, window panes for automobiles, and also why glass is used for building coating. And also here we can see silicon. But these materials are all high strength, but they have a low fracture toughness. What does it mean? So they are strong, but the energy you need to destroy them is very low. How can you explain this? If you have a normal constructional steel, which is somewhere from here, from that range, you could say, if you deform this, the deformation will be all over the part where the stress is above the yield strength. On the other hand, in a brittle material, yielding is not so important, but we have a crack which just propagates through the material. So in German you would say knacks, and then it's broken. And that means the energy you need to destroy it is low. And so we have already two parameters. One is the fracture toughness, and the second is the yield strength, or the ultimate tensile strength we have to take into account. Okay, now next I will skip it a little. In many technical parts we have notches. Even if we have such a small transition in thickness, that acts like a notch, and that always means at all such edge-like structures we will always have a stress concentration. That means if either the shape is not uniform, or on the other hand, if we have a transition of material, for instance, that would mean something like that. Here we would have another material. Also, such transition can lead to stress concentrations. And we must take this into account, because stress concentration always means the local stress is higher than we expect just from the overall stress. And if it is higher, then always the danger of fracture is increased. Okay, I will not go into the details. In notches, we use a notch factor, but let us skip this. But come back to the fatigue. So cracks are bad. Cracks in combination with fatigue are worse. So fatigue is one of the major causes of failures in materials, and most of the failures during service are caused by fatigue. That means it is not the unique overstress in most cases, but in most cases it is just the repetition of stress, for instance, or stress concentration. Here this citation says in the 20th century about 10,000 publications on fatigue were made. I think it will be more, but you can see it was quite a lot. It just must be taken into account how many different materials we have, and for each material we must have a characterization of the fatigue behavior. So the fatigue phenomenon was detected in the 19th century, let's say around the year 1860 or so. And what makes me somewhat sad is that this severe accident in Germany was just a 19th century accident. And the German railroad engineer August Wöhler he first proposed a method to deal with fatigue failures, and in America it was Mr. Baskin. And this representation of the fatigue curve is the so-called SN curve or Wöhler curve. Okay, now let's come back to the stress. We typically can have a lower stress and a higher stress. In the most simple case, it is, for instance, minus, let's say, for instance, 100 megapascal to plus 100, so it's a symmetric. But we can also have asymmetric behavior, so we are in the tensile region, so we have a superposition of tension, or we have a superposition of compression. So one of the questions to you might be, what is worse when we have alternating stress, when we have a superposition of tension or a superposition of compression? What is worse? Could be a question in an exam, for instance. And do you have a simple idea what could be worse? So if you look at a crack, normally a crack is opened by stress, but it is not, it is closed again by compression, but this closure of the crack will not do any damage. A crack will only propagate when it is under tension or under shear, and that means with a clever superposition of compressive stresses, we can avoid that cracks can propagate. That's, for instance, the trick in high-strength glass we used in facades or so. This glass is hardened in a way that on the surface we have always compressive stress, and as cracks always start from the surface, all cracks which could be there are always closed by the compressive stress. And that means the survival probability will be very high. But now let's come back to Mr. Wöhler. And here we have the stress amplitude. And now Mr. Wöhler did a number of experiments. He took a steel rod, for instance, and that rod can be tested in tension and compression, or you can also bend it and turn it. So on the surface you have always compressive stress, tensile stress, compressive, and so on. And when you take that stress amplitude and make, for instance, a number of experiments with a certain stress amplitude, you end up with results. How many revolutions your sample will tolerate. But at a certain stress level, you can sometimes find you can test almost until infinity. That means then you have reached some kind of fatigue limit below which there will be no more damage. Fatigue limit is typically in materials when there is really only elastic deformation and there are no more internal, let's say, movements or reactions in the chemical structure. And in that way, Mr. Wöhler could construct such a curve. And now, when you have such a curve, you have this falling branch of this curve, and then you have the horizontal. So And below that fatigue limit, there is in many materials no longer a fatigue process, and so this can live until infinity. Okay, in that way, you can already construct that such a curve. A rule of thumb is you need at least 7 to 10 test specimens, and then you get a first preliminary idea of the behavior. What is also important is the scatter is significant. You must note that this is a logarithmic scale, and typically this Wöhler curve you see here is for a failure probability of 50%. So it's you could say it's the average number of cycles for that stress level or that stress amplitude level. And now let's have a look into the material. When we again plot here the number of cycles or log number of cycles, we have first a crack-free phase. So let's think that is the material and here is the surface. And in the crack-free phase, nothing will happen, but we can have in the material some dislocation movement. Typically it's on some gliding bands, and they are typically under 45 degrees because here shear stress is maximum, and that typically can lead to some stepwise very small crack. That's especially in metal parts, but also in ceramics. So we have a crack initiation. And we have seen that even a very small crack in a brittle material decreases strength significantly. So after a certain phase, we have a very small crack, let's say in the 1 micrometer range or so. You can even see it when you have a polished sample. It suddenly gets a little rougher. And then we have the crack propagation phase. And here a crack, it will grow. It typically can grow always faster. And at some point, when it has gone through a significant part of the specimen, it will crack suddenly, and that is the fracture. So that means in the crack propagation phase, it is not necessary that the crack goes all through the part, but only until a critical limit is reached, and then it will fracture completely. Okay, that's such a process, and such a process, of course, is it's a good thing that we can know how it works, but on the other hand, as soon as a crack starts to propagate, it can become very dangerous. Cracks can have different behavior. For instance, we can have a stable crack propagation in a ductile material, so we just bend it or pull it until it's pulled apart. That would be a stable crack propagation. We can have a continuous crack growth, so that means in a cyclic behavior, in fatigue, or we can have an unstable fracture. That means at some point of load, the sample will just suddenly break. Unfortunately, it is not that these processes are independent, but what we have seen in the train was a combination of these both. Yeah, first fatigue, and then in the end, because it was in that steel part, we had in the end we had the brittle fracture. Also, what can happen is a crack can be arrested, so it can be trapped, and a crack can be arrested in compressive zone. Again, the crack propagates, but if it's a complex part, the crack can wander into a region where there is compressive stress, and then the crack can no longer propagate, and here it is a so-called arrested or trapped crack. Okay, so we see alone that is quite complex, and that is only for the behavior of fracture in a single part. Again, here we see the SN curve or Baskin's curve again. So again, that is important. That also could be a question in the exam. What would be the SN curve of a steel? And here you could say that is relatively easy to construct. We can say here typically the boundary is half a cycle. So that means when we just pull the part, we just pull it. It is not really fatigue, but the stress level can typically not be higher than the yield stress. So here we have half a cycle, here we have a log cycle, and then from the yield stress it goes more or less in a linear curve when we have the stress amplitude here, either in a linear or in Baskin in a logarithmic way, and here we typically have 10 to the power of 7 cycles. And so we have this slope going down, and the endurance limit or the fatigue limit is typically 0.4 to 0.6 of sigma yield. And in that way, we can construct such a Baskin curve for a material where we have no more information. For instance, such a thing I would do maybe for a steel or for another material, but it is also important that we know the material really has an endurance limit. Some materials do not have an endurance limit, like aluminum, for instance, and steel also has not an endurance limit when we have combined corrosion, for instance. Okay, we must keep in mind this is only for pure mechanical testing under relatively normal environmental conditions. No extreme low temperature, no extreme high temperature, no corrosive attack. So I say here, for instance, typically for a steel. But on the other hand, we have an idea how such a SN curve is constructed, and on the other hand, that is just to have an idea. It is important, of course, to measure such data. I had a PhD student whose task was to test very small specimens, and these small specimens were, the fatigue was tested in that region here, and so in that way we just loaded it in up and down, and the question is how can you do it with a small part, and it was a a tricky thing. In fact, I must say it was a very good idea. We glued a very small magnet here, and we put a coil underneath, and on that coil we put a alternating voltage, and in that way we could deflect this bar, and in that way the stress here, so that's the stress we see here, was can be seen, and in that way, as you can see here again, here where the stress is maximum, we can do fatigue investigation for very, very small parts. And again, here is our endurance limit. In that case, it was a special stainless steel, and we investigated the question if it was an etched part. So it was etched with photolithography from a thin foil, and that EDM was machined with electric discharge, which is also a convenient method. And in that way, for instance, the fatigue curve of such material was found. What was a little surprising is that the etched part, which had a much better surface quality, failed earlier than the EDM steel. Here, that was a rapid prototyping material, and here in that material we had a similar endurance limit, but on the other hand, in the time or at stresses in lower times and higher stresses, we had a very large scatter. Yeah, if you compare it here, the scatter for the blue or the black is very low, and here it's very large. And again, the scatter is affected by internal defects. So that's the reason why I myself am not so keen of rapid prototyping parts, because into such parts you can easily build in internal defects which you do not see, but according to that Snedden equation, at each defect you have a stress increase, and that means the overall strength and also the overall lifetime of such parts with defects is reduced. So it's the same thing like we have in that railroad wheel, but the situation is significantly worse when we already have built-in defects from production. And that later on again will be an important part. So always defects which we build into a specimen during production are a severe risk factor, which can, as we see, it can reduce the lifetime here by almost 2 orders of magnitude. So you could say in an optimum part you have something like 2 million of cycles, and here in that case maybe you just have 70,000 cycles. So that's a big difference. So that would mean in one case your car will live 300,000 kilometers, and in the other case it will break down at 15,000 kilometers. It's already something to mention. Here we also did it for copper. For instance, we investigated what the effect of several processes is when the copper is produced. For instance, we had electroplated copper under different conditions. We had copper surface which is rough, EDM laser cut etched, and so on. And here that was really polished, and it again shows us when the surface is very shiny, glossy, no defects on the surface, and when at the same time there are no internal defects, the lifetime will be very high. And again, in that case, we can find Baskin's equation again. Here we have that is just pure copper. We have a yield somewhere around 250, and we have, on the other hand, endurance limit of, you could say, more or less roughly at 50% of that yield. So again, the transition, as I said, it's around 10 to the power of 7, or rather in the middle between 10 to the power of 6 and 10 to the power of 7 cycles. And in that way, it demonstrates that fatigue is a very important phenomenon. And again, I must say, stress level of 125 is a stress level that can easily be produced by assembly and packaging processes. Okay. Now, another of my PhD students, he was dealing with the question how vibration is changing, because when we look at Wöhler's curve, it is important that to know that this curve was taken up under conditions where we always had one stress amplitude. Yeah, here one stress amplitude, another stress amplitude, another, but the stress amplitude is constant. But when we look here at accelerations in a car, that was a Mercedes we had at that time as a test part, and my PhD students, they liked it very much that we had that test car, because it has roughly 300 horsepower, and the fuel was paid by Mercedes company, so we had some fun with these test drives. And so what was the result here? The result was that accelerations and at the same time stress levels will vary in a very complex way. And the question is, how can we predict now the lifetime of some part subjected to fatigue under variable conditions? Do you have an idea how we could do that? There is an idea which counts the consumption of lifetime. Imagine under a certain condition, let's say 150 megapascal, we would live for 2 million of cycles. Yeah. When we have tested up to at 150 megapascal, when we have tested for 1 million of cycles, how much of the lifetime did we consume? Okay, again, the question, at a certain condition, like let's say 150 megapascal, it would live for 2 million cycles, and we test for 1 million cycles. How much of the lifetime did we consume? On the other hand, let's go to 200 megapascal. Here it is, let's say, what is it? 600,000 cycles. And we test for 300,000. Again, we would consume 50% of lifetime. Yeah? So that would mean, for instance, if we test to half of it, so that would be 50%. And here, here it was from that, we go to half of it, so it would be 50%. So if we test to 50% here and 50% here, we would have to expect that it will fail. And that is the so-called life fractional rule. So the idea is we look for a certain load amplitude in our spectral distribution, and then we just compute how much of the lifetime it will consume. And all of the lifetime consumptions will be added up, and in that way we can find out how many load cycles we will be able to tolerate, and that is the so-called Palmgren minor rule. So that means we have a damage, and the individual damage is the number of cycles we tested divided by the number of cycles to failure under the same condition. And now we take our stress range we find. For instance, here we have different stress ranges, and for each stress range we count the number of cycles and divide it by the number of cycles under the same conditions. And then we could say, okay, when we have 5 stress levels, for instance, then we can always count the number of cycles. We also know how many cycles it will be until it fails. And in that way, we can compute the individual damages, and we add up all damages, and in that way we can say when the total damage reaches 100%, then we can expect our part will fail. And that Palmgren minor rule is the easiest way to predict fatigue lifetime under conditions of variable testing or under variable service conditions. Okay, I think we will have to treat it in the exercise, but on the other hand, that is a concept which can also be used for other types of failure. So it is not only restricted to mechanical failure by fatigue, but it can also be used for instance, for electrical load, for failure which is a result of high field strength or so. Okay, in that way, we are able to predict the lifetime, and in our case, I will not go into the details, but we can see having a certain range of tests, then we can extrapolate how many cycles it can tolerate in the field, and the field is defined by variable load conditions. On the other hand, it is also important to know when we do such an extrapolation, when we only do a very slight variation here in the interpolation range, it can lead to an extremely large mistake we make in the extrapolation. That's the backdraw of that method. Okay, in that way,